Hello everyone, I'm Chen, a PhD candidate in Harbin Institute of Technology. Today, I'm introducing our research on behalf of all my co-authors. Our research title is Accurate ICR Quantization for Uplink Multi-User NOMA System. Here are the contents. The first is background and motivation of this research, then the system model, ICR quantization, numerical results, and conclusion. New radio access technologies are available, especially targeting the connectivity requirements of massive Internet of Things applications. Secular IoT technologies will drive the digitalization of society by delivering machine-to-machine on a massive scale. As shown in this figure, Ericsson predicts that there will be 5 billion IoT devices by 2025 connected via secure 3GPP access technologies. Compared with the traditional OMA schemes, the NOMA transmission schemes exhibit the following advantages. The first is high bandwidth efficiency. NOMA exhibits a high bandwidth efficiency and hence improves the system's throughput, which is attributed to the fact that NOMA allows each resource block to be exploited by multiple users. The second is fairness. A key feature of NOMA is that it allocates more power to the weak users. By doing so, NOMA is capable of guaranteeing an attractive trade-off between the fairness among users in terms of their throughput. The third is ultra-high connectivity. The future communication system is expected to support the connection of billions of smart devices in the IoT. The existence of NOMA offers a promising design alternative for efficiently solving this task by exploiting its non-thermal characteristics. OMA requires the same number of resource blocks as the number of devices, while NOMA is capable of serving these devices using less resource blocks. The fourth is compatibility. From a theoretical perspective, NOMA can be invoked as an add-on technology for any existing OMA techniques, due to the fact that it exploits a new dimension, namely the power domain. The basic principle of NOMA technology rely on the employment of superposition coding at the transmitter and successive interference cancellation at the receiver. Due to its potential, NOMA is studied thoroughly in recent years. Among these contributions, many problems are addressed from the perspective of system performance, such as system capacity and outage probability based on the Shannon formula. Channel codes currently used are designed to approach the channel capacity for long data packets. However, the transmission of small data packets associated with IoT poses a challenge. That is, due to the significant performance degradation. We cannot use the channel codes to approach the channel capacity of the NOMA system. In this regard, evaluating the error rate performance helps to develop effective algorithm which can be utilized to improve the performance of the entire NOMA system. Here is an Uplink NOMA system with L users and one base station. For simplicity, we assume that both the base station and the MTC devices are equipped with a single antenna. All users adopt the same modulation, that is BPSK or QPSK. Besides, the carrier is recovered perfectly and the symbol is synchronized at the BS. We suppose that different users are multiplexed in the power domain by transmitting equal maximum power. Because of their different channel conditions, their received power at the BS is different. Therefore, the superimposed received signal at the BS is given by equation 1, without loss of generated. We assume that users are sorted in ascending order according to their received power. At the BS, the receiver adopts SIC to decode all users' data. The user signal, which has the strongest power, is detected first while treating other signals as interference. The first user signal is detected using maximum likelihood detection, according to the following rule in equation 2. Once the receiver decodes SL correctly, it reconstructs XL and subtracts XL from the received signal Y. Repeating this operation in descending order according to their received power, until all users' information has been decoded. Since the received signal of the first user is interfered by the rest L-1 user signals, the BS should select users whose channel conditions are significantly different and multiply them in the power domain. The process of demodulating is given as equation 4. If the message of previous users are not correctly decoded at the receiver, the wrong reconstructed signal is subtracted from the composite multi-user signal, thus resulting in interference to the remaining users. It leads to accumulation of decoding errors. The error propagation problem of SIC makes SER quantization for the NOMA systems intractable. We derived the expression of the SER performance for NOMA system. First, we quantify SER performance focused on 2 user cases. Then we extend the multi-user cases. For simplicity, we assume that all users adopt BPSK modulated signals. Theorem 1 is our main result in the SER performance of 2-user uplink NOMA system. The receiver decodes S2 while treating S1 as interference. The SER of user 2 is calculated as equation 8. When U2 signal is correctly decoded, the SER of U1 can be expressed as equation 9. The receiver adopts SIC to decode S2, reconstructs and subtracts S2 from the received signal, as shown in equation 9. Similarly, when U2 signal is incorrectly decoded, the SER of U1 can be expressed as equation 10. The total SER of U1 can be expressed as equation 11. Thus, equation 7 is 15. In multi-user case, theorem 2 is our main result that SER performance of multi-user uplink system. The derivation process of equation 12 is similar to equation 8. For L greater than 1, the SER can be expressed as equation 15. LB is the lower bound of the integration interval and can be calculated as equation 17. M is the intermediate variable and can be calculated as equation 18. We substitute equation 16 to equation 18 into equation 15. Then we can obtain equation 13 and 14. Several sets of experiments using Monte Carlo simulation are designed to verify the expression obtained beforehand. We first show the limitations of the approximate expression, which we call the approximate results, through the case of a two-user NOMA system. Then we show that our quantization expression is effective under multi-user cases. We show the SER performance comparison between our method and the appropriate quantization method through a two-user NOMA system. In this experiment, we changed the received power user 1 while keeping the received power of user 2 unchanged. Both users adopt DPSK modulation. Monte Carlo simulation results, our quantified expression and approximate quantified expression show consistency in this figure. However, in this figure, the approximate quantization method cannot fit the SER performance curve of user 1. It is only suitable for occasions where the error propagation phenomenon is not obvious and cannot accurately quantify the performance. Next, this figure shows the SER performance curve of 4-user NOMA system. Our users adopt DPSK modulation. It shows perfect consistency between our expression and Monte Carlo simulation. In our experiments, we changed the received power of user 1 while keeping the received power of other users unchanged. To explore the relationship between the SER performance of each user and the corresponding received power, it can be observed from the figure that the SER performance of the other users decreases as the received power increases. This is because the other users are being decoded. User 1's signal is regarded as interference. The stronger the power of U1, the stronger the interference, which causes performance degradation. Meanwhile, the SER of U1 increases and then decreases as the received power increases. The main reason for this phenomenon is that when the received power is lower than 5 dB, the SER performance improves as the signal power increases. When the received power exceeds 5 dB, The extra power causes previous users to suffer more interference during decoding. In the decoding process of U1, the performance degradation caused by error propagation exceeds the performance improvement brought about by the increase of its power. So the overall performance is degraded. We use the same experimental method to explore the performance of the QPSK case. In this figure, the SER performance of the 5-user NOMA system is tested. In this experiment, we change the received power user 2 while keeping the received power of other users constant. The received power settings of other users are as follows. From the figure, we can draw the same conclusion as before. It is worth noting that when the received power of user 2 is higher, we mean greater than 14 dB, the SER curves of U1, user 2, and user 3 coincide. This is because in this case, the error propagation phenomenon is severe, and the decoding failure of the previous user almost certainly causes the decoding failure of its subsequent users. As can be seen from this figure, our quantified expression can fit the performance curve accurately, even when the error propagation is severe. That confirms the effectiveness. Here is the conclusion of our research. NOMA is identified as a promising technology for massive IoT applications. This paper quantified the SER performance accurately for the Uplink multi-user NOMA system over the AWGN channel. The corresponding simulation results verified the correctness of the derived expression. Based on the expression proposed in this paper, we can solve many problems effectively, which cannot be solved by the traditional Shannon formula, thus improve the performance of the entire system. Thank you for listening.